So let us continue with planning. So in the last lecture we have seen partial order planning. Today we'll be looking into a different data structure known as planning graphs, where we generate the plan over a graph. So we'll be elaborating on top of that. So earlier what we have in the partial planning, what we have done, we have the initial state, we have the goal state, we look into the goals, sub goal, so we find out the sub goals in the goal state, and then we try to achieve those sub goals by searching over uh, the different actions that we can actually apply. And once we find out those things, then we try to order all those actions, because sometimes we have seen that if we if we uh, if we make an action, then that can create a effect which may conflict with some other action, so we have to be careful. So sometimes we can make a total ordering, sometimes we can have a partial ordering also, depending on the problem. So in planning graphs, what we'll be doing will be creating a sequence of labels. So one of sequence of labels. So in one of the label, I'll be having the set of actions, and in another level I will have the set of literals, and that will keep on unfolding over time or the different levels. So which will be clear once we go into an example. So the thing that I would like to highlight here is that it will contain labels of a set of actions and a set of literals. So this set of literals basically denotes the states, and when we apply this action, it creates when we apply this action on the set of literals, it will create a new states, and that will keep on unfolding over time. And one of the important thing that we need to add, that sometimes we'll be adding a specialized action that I will elaborate in the next slide, which is known as the persistent action, which effectively means that uh, when I have a literals and I do not transform it to any other new form, I just want to continue with that literals as it is. Why it will be required, that will be clear in the next slide. So let us look into one such examples, how we can create the planning graph, and from how what are the things we need to take care of. So let us consider a very simple problem, that I have been given a start state with have cake, and I want to achieve a situation which is my goal state is the have cake and eaten cake. The set of actions that have been provided to me are I can eat the cake, one option. So eat cake comes with one of the precondition that it should have a cake, and once you apply that action, you end up with eaten cake state, and you have no longer the cake with you. The other action that have been provided is the bake cake. So bake cake you can actually apply when you do not have the cake, that is not have cake is true, and as a result, once you uh, do a baking of cake, then you have the cake after the action bake cake. So for this simple problem, we will be creating the complete planning graph. So as we said that in order to create this planning graph, we need to create the label. So initially I have this information only, that is the have cake. So that is my initial state. From this initial state we can apply different actions, and we can create a new states. So we'll be creating labels of literals and the actions. So let us start. So in the beginning, I have I'm in so when I am in a state, I'll be representing with S, and when I'm applying an action, then I will be representing with a notation of A. So S0 is the initial label where we represent only the literals or only the proposition that I have. So in the start set, I have been given have cake, and we actually add all the other unlisted literals in the negated form. So whatever literals have not been specified, that will be treated as the negative in the negative form, and that will be added in our representation. So in the start state we have cake and nothing has been mentioned, and we have only two literals, so we add the not eaten cake. So that will be my first label. So in the next level, what we are going to do, we are will have the set of actions. Now in the next state, when we try to when we have the action, then there are two possible actions that we can actually apply. So there is a complete set. I can apply either eat cake or bake cake in every actions uh, level, but depending on the precondition that are available to me, it may happen that all the actions are not activated. For example, in the first level of actions, I eat cake is can be activated because it has the have cake, but bake cake I cannot apply in the level A0 because it requires not have cake, which is not true. So therefore we can only apply eat cake at the very first level of actions. Now once we so this can be so eat cake can be applied because have cake is true in the previous level. Now if we apply eat cake, then it results into a set of new literals, which is not have cake and the eaten cake, that we can figure it out from the effects of the corresponding action. So the moment we apply eat cake, it results into two literals, as in this case not have cake and the eaten cake. Fine. Now, so what we are doing here, so we have the initial state, we apply some action, and we get a new state. So it is on nothing but we are actually expanding our horizon, and we are creating the new set of states by applying the possible action. Now at the level of S1, we have only not have and eaten. So this is the results only when we apply this eat cake, and no other action is possible at the level of A0. But another thing to note here, that if we try to apply a new actions in the next level for my A1, then only then I have to check for what are the actions that I can actually make depending on the literals that are available in this level. Now here the thing is that in S1 level I do not have a situation have cake, but if you think a little bit, let's say I have so as of now we have cake in the S0, and if we do not apply this action eat cake, though it is applicable, but let's say I do not apply have cake, then this will end up with have cake in this state, because no action is also an action that I can think of. And then I can explore the all possible actions that I can make over this set of literals, because if I do not add this have cake here, then I'm basically restricting my the setups the these literals and the states that I am actually and that I can actually express. So what I need to do, I need to pass on these literals as it is in the next level, and that we can do with by making no actions, and which is called the persistence action. So whatever was there, it will pass it on in the next level as it is, and we represent such an action as called the persistent action with a simple box. So that means in this level we can apply eat cake, we can also apply as a persistent action, also similarly for this persistent action. So in this level I will have all possible literals that I can actually achieve, and which is actually logical because some of the literals will be generated from applying some action, and some of the literals will carry forward as it is. Now, one of the important thing to note here is that 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 we are saying that this set of literals these set of literals can be generated by applying the set of actions here on the initial state. Now if you look into the set of literals that are being generated, like have cake and not have cake, so in this state at S1 I cannot have a situation uh, where both of them are true simultaneously. I cannot have a situation that both of them are true simultaneously. Similarly, here if you look into, I have eaten cake and not eaten cake. So at a particular state, I cannot have both uh, both the literals to be true. And why is this situation that we are achieving? Because we have added the persistent actions, so we are just carry forwarding as it is. So therefore we need to do something else so that we can actually say that these two uh, these two literals will not be true simultaneously. So and and the thing is that we cannot reach to such a state where I have cake and not have cake both are true. So we need to restrict that. In order to restrict that, what we can do, or what we can actually say, that that we are when we have these two literals, we say that these two literals are generated based on the action this and this. But the thing is that these two action cannot happen together, they are mutually exclusive action, because if I carry forward this have cake as it is, that means I'm not applying eat cake. And if I have this eat cake action, then I cannot carry forward this have cake. So these two events are actually mutually exclusive event, because they results into two conflicting literals. so, so therefore we need to say that I have either these persistence actions will happen, or this actual action can take place. Similarly for this eaten cake actions and the eat cake, these two cannot happen simultaneously because they result into two conflicting literals. So and we will represent this mutual exclusive mutex actions through a line, something in will be drawn in red. So whatever actions I have in this level, I cannot apply all of those actions, and certain actions will be mutually exclusive. Okay, so now we will look into the state S1. Now here we have this mutex actions, and that results into certain things. So here we will have similarly some mutex literals, because I cannot achieve uh, these two literals simultaneously. So again we'll be representing the mutex literals in a similar manner. So how we can figure it out, the mutex literals? So what we can do, or the easiest thing is that that these two will be definitely in conflicting, so they will be the mutex literals, because if a literals appears in both positive and negative form, then they will be mutually exclusive. Both of them cannot be true together at a particular state. Similarly, these two will be mutually exclusive on the mutex literals. Now let us see what is the situation for have cake and the eaten cake. So if you look into these two literals, only have cake and eaten cake, then since these two are different literals, probably it may appear that we may not be able to say anything uh, about the mutex. Probably they are not mutex event. But if we take a deeper look, then this eaten cake is generated by this eat cake. This eaten cake is will be generated by eat cake, and this have cake will be generated by this persistent action. So that is the only way I can have the have cake and the eaten cake. Now these two events, eat cake and the persistent actions, are mutually exclusive. So therefore we cannot produce both have cake and eaten cake together, because they will be generated from two mutually exclusive actions. So therefore have cake and eaten cake will be mutually exclusive, or the mutex literals. Similarly, not have cake and eaten cake will be also will be mutually exclusive, because they are generated from two mutex action like eat cake and not eaten cake, which will be representing through the red line. Now from S1 we'll be again applying the set of actions, and we'll be generating the next set of literals. Now in the next level we will try to apply, we just need to check what are the action we can actually apply at this stage. Now here, if you look this, we have this set of literals. So eat cake is can be activated because it has the have cake. I can also apply bake cake because not have cake is also true at this level. So both the actions are actually applicable at this stage. And also we need to add all the four persistence actions, because they can move forward as it is. So effectively we can add two actions, and we can carry forward all those four persistence action. Now again here we have to check for the mutex action. So some of the actions that we can actually see what are some of the actions that we cannot make it together. So in order to identify those things, we may need to look into the stuff that it will be produced once we apply this thing. So when we apply eat cake, it results into not have cake and eaten cake. We and when we apply bake cake, it results into have cake. So now let us look into the mutual mutex actions. So if you look into bake cake, and if you look into bake cake and the eat cake, bake cake results into have cake, eat cake results into not have cake. So so they produce the conflicting literals, and at S2 only one of them can be true because both of them cannot be true together. So therefore we can say that bake cake and the eat cake are mutex actions. Similarly, for have cake and not have cake will be also mutex action because they produce the literals in the negated form. Have cake and eat cake also be mutually exclusive because they produce the conflicting literals, and so on and so forth. Similarly, on this part, uh, similarly on this front, like eaten cake and not eaten cake, they will be mutually exclusive because these two events are these two actions can only be generated uh, from this set of literals, and they are mutually exclusive. So uh, they are they are mutual mutex action. And also these two action, in another way we can look into these two actions results into conflicting literals. Similarly, another thing just to note here, that these persistent actions and these eat cake are also mutually exclusive, uh, because if I um, uh, because if I have cake, so if I so if I look into these two situations, so this eat cake results into not have cake, and this have cake results into a have cake. So if I apply these two actions together, then I cannot have cake with me because it will result into not have cake. So therefore these two actions are also mutually exclusive. They results into conflicting stuff. So so that will be the set of mutex action that we can represent here. Now we have to check for the uh, mutex literals. So here again these mutex literals, we will have these two will be mutex event, these two will be mutex literals because one of them is conflict with the other. And also to note here that these two literals will be conflicting because these two can be this can be generated uh, from. So when we look into not eaten cake and the ham cake, not eaten cake is a results from this eaten cake, and not have cake results from this eat cake, and these two events, these two actions are mutually exclusive. So I cannot have this situation, so either one of these action will take place, so I can have only not have cake, and I uh, I can have or not eaten cake. Now let us look into the situation that that we have seen earlier, like have cake and eaten cake. So earlier these two events were mutex uh, literals, but what is the situation now? An interesting thing to note here that this have cake and the eaten cake are my sub goals individually, and they can achieve, these two together can achieve the goal state. Now, this have cake, uh, this have cake can be generated from this bake cake. Fine. So this is an event which depends on the not have cake, and I can generate this have cake through this path. And this eaten cake is can be a persistent event that pass through as it is from the previous level. Now if you look into this action, this persistent action, eaten cake and the baked cake, they are mutually exclusive, so I do not have any issue for that. So these two literals are these two are can be generated together, so they are not mutex literals. And if they are not mutex literals, that mean I can have these two literals. uh, it's a possible that we achieve these two literals together uh, in state S2. So therefore we can look for some kind of a solutions, because we can achieve these two things together, so they are not mutex, so we can achieve this thing together. So we will try to figure out whether there is a set of actions that can really achieve these two literals together. So the main important point is that, so that this mutual exclusion relations over the literals is actually decreasing. Early in the initial stage, we have three such connectivity. Now we have earlier we have four such connectivities. Now we have three such dependency stubs for the mutex one. So one thing to note that here we have two literals we started with, and we end up with four literals here. Again we have four literals here, and you can easily understand that it will remain four literals throughout. So the count of literals will keep on increasing, so it's kind of a monotonically increasing. It may saturate, but it will keep on increasing, it will never decrease. The actions that we have applied here is the only actions available to me. The persistence actions will keep on adding, and here we can apply one more actions, eat cake and the bake cake. So the number of actions that we can make is also monotonically increasing, but the mutual exclusion over the literals will keep on decreasing. Fine. So this will help us to mm, uh, prove some results which will not prove here, but we will state that fact. So another thing we would like to highlight here. So for a problem, what we would like to do, that we start with the set of literals, we apply the actions, we generate the next set of literals, and from the next set of literals we apply the actions and generate the next set of literals, and so on and so forth. And in every levels we maintain the mutual exclusion relations. And once we reach to a situation that this we achieve non-mutex literals that represent the goal state, we will try to figure out whether there exists a solution or not. So it may happen that even if we have reached to a situation that these two are non-mutex, but still we may not be able to find out any such um, uh, any such planning to achieve these two things together because of some other constraint. So if it happens in that scenario, if it's happened to be that scenario, then what we do, we apply the actions one more time, and then we generate the next set of uh, literals, and we check whether we can achieve those non-mutex literals from state S3 or not, and so on and so forth. So the overall strategy of this algorithm is that we apply set of actions, we generate the literals, we check for non-mutex literals that represent the goal state. If it's so, we try to find out the solution. If we fail to find out the solutions, then we expand the horizon by one more level, and we repeat the same stuff. So the obvious question is that when to stop. The interesting thing is that if we end up a situation, if we have a situation like when two consecutive states, like for examples, let's say S1 and S2 or S2 and S3, if they results into the same scenario, like the set of literals along with the mutex information, if I end up with the same states, then we can say that uh, we cannot explore any more, we do not need to explore any further, because even if we apply any actions, it will result into the same situations. So at that point of time, we will actually stop, and we can, and if we cannot find out any uh, plan for that situation, then we say that it is a failure. So these are the mutex literals. So here we have reached to a situation that we achieve non-mutex literals that represent the goal state. So we'll be looking into how to generate the plan for that. We'll see. So before generating the plan, let us quickly look into what is the mutex action. So it is mutual exclusion relation exists between two actions if any one of these three actually hold. We have actually already seen. So one is the inconsistent effect. So what does that mean? That one action negates an effect of the other. So if you look into this eat cake, eat cake and the bake cake, they results into not have cake and have cake. So eat cake results into not have cake, bake cake results into have cake, and so one of them is the negative of the other, so they are actually inconsistent. So they are they are they have to be mutex action. There can be a situation like interference. So one of the effects of one action is the negation of a precondition of the other. For example, if you look into this eat cake and the have cake, so eat cake results into not have cake, and have cake results into have cake, which is the mm, so so it requires have cake as the precondition, and this results into not have cake. So one of the effects of one action is the negation of the precondition of the other, so which is actually hold here. So so therefore eat cake and the have cake are mutually exclusive. And also there are sometimes like a competing needs. So one of the preconditions of one actions is mutually exclusive with the precondition of the other. So like if you look into the bake cake and the eat cake depends on ham cake and bake cake depends on not ham cake, and they are mutually exclusive. So therefore these two um, uh, actions are mutually exclusive. So so by looking into the precondition and the effects, we can figure it out what are uh, what are the actions that we can what are the actions that can take place together. Similarly for not exactly same, but for mutex literals, uh, this relation exists between two literals if one is the negation of others that we have already talked about, and each possible pair of actions that could achieve the two literals is mutually exclusive. Like say, here we have said that have cake and the eaten cake is mutually exclusive because it is being generated through these persistent actions and these actions, and these actions are mutually exclusive, so therefore these two are mutually exclusive. But in this situation, this have cake can be generated from the baked cake, and not eaten cake can be generated from the persistent action, this one, and these two are not uh, mutex actions, so therefore they are not mutex literals. So so the overall algorithm, the way it will actually work is we take the initial problem, we generate the goal state from the given problem. So what we do, if goals are all non-mutex in the last level of the graph, then we try to find out the solution. If we obtain a solution which is if we have a failure, then if we cannot find out a solutions, then we can return the solutions, and if no solution is possible, then we return the failure on the graph, or otherwise we actually expand the graph and we repeat the same steps. So when to terminate, uh, how we can identify. So so one of the thing that we have talked about, that the literals will increase monotonically, the actions will increase monotonically, but the mutex will decrease monotonically. So if we keep on applying this stuff, at some point of time we will reach to the same state, and if the two consecutive states are the same, then we need to stop at that point of time. Now let us look into how we can generate the actual plan, that is the one of the main major objective. So so once we find out all goal predicates without mutex, which is true at S2, the plan can be extracted by solving a constraint satisfaction problem. Because what what we have the situation that we can generate these literals by applying certain set of actions, which are some of the actions are the mutex actions. So we have to choose the appropriate ordering so that we can maintain the mutex or mutex relations among the actions, and still we are able to achieve this one. And so there will be a lot of combinations, and we can, so that problem can be modeled as a constraint satisfaction problem. So one thing to note here is the creating the planning graph can be done in polynomial time, because the size, typically the size for a search tree that we have seen in the first set of lectures of this course, which the tree grows exponentially. Here the size of the graph is limited because the number of literals will reach to a certain point. But the so the creating the planning graph can be done in polynomial time, but the planning is known to be p-space complete problem. We will not go into what does that mean, but if you are interested, you can just look into. So the thing is, the hardness comes from finding out the plan, because we need to solve through a CSP problem, so which is actually a hard problem. So now we try to find out the plan. So we have this have cake and the eaten cake is true at this level, and is 2. Now these two can be this head cake is a result from the baked cake, and this eaten cake can results from a persistent action, this one. We so here this eaten cake can be results from this eat cake, but we do not choose the eat cake because eat cake and the bake cake are mutually exclusive, so these two events cannot happen together. So we choose eaten cake for this one. So there is also option that have cake can come from have cake, but if we if we we can also explore that one also, like have cake is coming from have this one, eaten cake is coming from this eaten one. But here then I will be in trouble because eaten cake and this have cake is mutually exclusive. So therefore we are not exploring that part. So ham cake is coming from baked cake, eaten cake is coming from this persistent action. Fine. So we reach to this not ham cake and the eaten cake, and these two literals can be produced from this eat cake, and this eat cake can be produced from the this ham cake. So we have been given with these initial conditions, and we reach to the stuff. And if we select this plan, then at every level the actions are mutually exclusive, so we are honoring the basic requirement. So we can figure it out, we can find out the plan by solving a CSP problem. Now we will move into a different way of modeling the problem through through the propositional logic, and more specifically through SAT based technique. Earlier in this course we have seen that SAT is an important is a very powerful technique which can be used to solve many hard problem that we have seen in the earlier lectures. So here what we will be doing, we will be modeling this planning problem as a SAT problem, and we will be using the notion of the graph plan, and we will try to model uh, this problem this technique using the SAT or the Boolean logic. So the planning problem is translated into CNF satisfiability problem, and the goal is ascertained to hold at time step t. So if you remember, in the graph plan we are expanding step by step. Similarly for this CNF modeling, we try to reason, or we try to find out a solution which is at a depth of time step t. So that means we need to unfold t number of units, and then we try to figure out the final we try to find out the solution after unfolding up to time step t. And the clauses are included for each time step up to t. So what does that mean? It will be clear in a moment. So we need to generate the clauses up to timestamp t, and if the clauses are satisfiable, and if we extract out a plan, uh, uh, then we can if the clauses are actually satisfied, then a plan is extracted by examining the actions that are true. And if it's not satisfiable, then we increment t and we repeat the same steps. So something similar to the graph plan. Only difference is that we have to generate the CNF for each of the uh, clauses. So how to generate that we will see. So one of the thing that I would like to highlight here. So uh, we have the state S0, we have the action A0, then we move to S1, and then we have action A1, and so on and so forth. What we'll be doing here, that in so for every state we will have the set of literals. So if so this literals means like have cake or not have cake. Maybe here I can have the have cake. So here I have a have cake. Again I have cake here also, that we have seen. So what I would like to do, we have to express these literals, and we have to express these literals over time. So what we would like to do, in the literals we would like to introduce one more parameter that will represent the time. So earlier we are representing only with have cake. Now here we will be representing this have cake um, with a variable, something like have c cake, and this is the timestamp 1. So this variable will be represented by introducing the time parameter to that stuff. So we will have the set of boolean variables at every level. Similarly, we will have the actions that will also come with a suffix of time, or the level at which we are actually applying. So if I have an action A, if I am applying at time 0, then it will be A0, and I can apply the same action at other time point, and that, so we need to distinguish the actions across the time. So we will introduce a time parameter also for the action as well. So in order to construct the formulas to encode the bounded planning problem into a satisfiability problem, what we would like to do, like if we have a fluent at m, so earlier we talked about this propositions, we are saying it's a fluent because the value of at m can get changed over time, so which is the terminology. So let's say we represent this at m, which is our proposition, and we call we say that it is a fluent f. Just to reduce the space, we use f notation here. So this fluent will get converted into at m and I. We talked about that we have to introduce a parameter, the timestamp. So we represent this at mi as fi. So I denotes the timestamp. Similarly for actions, if I have a move ab, then we write is move ab at the time step I, and we'll be using a shorthand notation like ai, just to represent that action a has been applied or not applied at the I timestamps, depending on this the value 0 or 1. So we'll be writing the set of clauses, but we'll be using few notation just to uh, mm, just I would like to mention here. So this spelling is wrong. So we'll be using PC for precondition, E for effects. E plus will be the set of literals that are in the positive form in the effects list. Similarly for E minus, it will be the set of literals in the effects that are in the negated form. S0 will be denoting the start state, G will be the goal state, G plus will denote the literals in the positive form in the goal state, and similarly G minus, it will be the set of literals that are in the negative form in the goal state, and A will represent the set of all actions. So we need to build the SAT encoding. We'll be using the previous notations. So initial state. So here the we have been will be provided with set of literals that are true at a particular in the beginning. So all those things will be logically ANDed, and the set of literals that will not be specified will be added in the encoding through the negated operations. So that will be the clause. So that will be the clause for the initial state. For goal state, it will be similar. Only thing is that whatever clause have been specified, that will be adding at the level at the time step t, because we are expanding or we are looking for a solution up to depth t t t time steps. So therefore we just add ft, and if f belongs to negated operator, then it will be also added. So here we do not put the negated sign because f belongs to g minus, so therefore it will be in that form. Here if was not mentioned, and if does not belong to s0, so therefore we need to put that negation operator. So this will be my goal state. Then the action. The action, to represent this action, we know that there will be some precondition. If it's true, then we can actually apply actions and it results into some kinds of effects. So when we apply some actions AI, the effects that we'll be observing at I plus 1th step, right? And some condition needs to be true to apply certain actions. So some precondition have to be true. So what we say, that if action is true, or if I apply an action, that definitely implies that the preconditions of that action have to be true. And similarly, this action also implies that all the effects will be true as well. Here we do not write in the other way, like precondition implies this action, because even if the preconditions is true, I may not choose for that action, because if I write it that precondition implies these actions, that means whenever the precondition is true, I have to apply that action. But that may not be the case. I can apply actions uh, depending on my requirement, but this, if I apply these actions, then those have to be true definitely. So we write it in this manner. So this is one of the constant, and then we have to represent the a change of state, so which is one of the important thing. So in order to represent the change of state, what we do, that we consider the change of state. So that means propositions or the fluents has in the negated form in a particular state, and it becomes up in the positive form, or it is in the positive form in the current state, it goes into the negated form in the next state. So that's the thing that we have to represent. So that we can represent that we can say that whenever there is a change uh, in the proposition or the uh, fluent, then it is one of those actions that have to be taken place. So if there is a change, then the actions that belongs to uh, uh, that is the effect of a particular that the action have to be taken place for which this is the effect. So if I so it results into the positive form, then I should have an action in which if I belongs to the effects of AI, and that to belong in the positive form, and for all any one such action can lead to this fluent. Similarly for the negated form, so for all A, if I belongs to E minus of AI, and all such AI will be so if I have this situation, then this have to be true. Otherwise, if this action does not happen, then I will not be able to reach this one. So it's called the frame axiom. So it is the set of proposition that enumerate the set of actions that could have occurred in order to account for a state change. So in the graph plan, if you remember, then we talked about the mutual exclusion. Here we so we mutual exclusion. So two events cannot take place if they are mutually exclusive, but if they are not if they are not mutually exclusive, then I can have more than one events there. But here we just enforce the complete exclusion, which we make a strong condition that only one action can occur at each time step. So which is uh, theoretically fine. Only thing my solution can have more if I have a solution, the number of steps can get increased, but if the solution exists, then we will be able to figure it out. So we call this as a complete exclusion axiom, which says that only one action can takes place at a time step. So if AI and BI are the two actions at a particular time steps, then this will hold. So this effectively means not of AI and BI. So two events cannot happen simultaneously. So in order to solve this problem, we have to solve the satisfiability for this condition. So this will be my final set of clauses, and we have to check for the satisfiability of this problem. So so this is an exercise that you can do at your home. So this is a simple example. We have one robo R and two location L1 and L2. So let us suppose that the robo can move between two locations. In the initial state, the robo is at L1, and in the goal state it is at L2. The operator that moves the robo is actions move R, L and L prime. So L prime is the new location. The preconditions that it has to be in L effects it has is it reached to a new location and it's no longer in the initial location. And just to elaborate for this problem, I can have a plan of length 1, the goal state. So you can try to write the set of constraint for this problem. So what we have seen that in this planning, so it involves search along with the logic, and also there is a change of state. So we looked into the planning problem where our environment is fully observable, deterministic and static. So the moment you relax any one of these criteria, the problem is pretty challenging one also. And also we have seen the planning graph, and also looked into the set based planning, and it has a lot of applications in the mini uh, domain like robotics and autonomous systems. Like if you have a space applications where certain things can go wrong and you do not know uh, uh, which what will happen, so you have to take a quick decisions and you have to plan accordingly. So uh, so so planning, so this type of technique can be applied there also. Hmm? Thank you.